Hi, welcome back to another episode of pH14, a very basic podcast. I'm Nathan,
I'm Ben.
and today we have with us Professor Carlini. How are you, Professor Carlini?
Doing well. Happy Labor Day.
Welcome.
Yeah. This episode is a little more special for Ben and I because Professor Carlini is effectively our boss because we work in her lab.
So we gotta be very, very, very careful.
Yes.
For at least the first, 2 minutes before we don't really care anymore.
Yeah, absolutely. Yeah, before the coffee kicks in.
Exactly.
So, Professor, we have to ask you, our first question is the sword on your wall. What is the story behind the sword on the wall?
That actually came from my PhD advisor's lab. So when I defended my PhD, I was presented with a sword that matched my personality. And in the Geneski lab where I graduated with my PhD, they present you with the sword as a joke on, as a play on this Finnish tradition where you're presented with a ceremonial top hat and a ceremonial sword. And eventually evolved to a sword that was specific to the individual. So some people get these Jon Snow broadswords, interesting daggers, rapiers, fencing swords, katanas, and my friends pulled together to surprise me with a batleth. So I'm a big Star Trek fan, and I have this really nice batleth Klingon battle sword hanging up right next to my degrees. So to me, that's my PhD.
It's kind of intimidating for anybody who just walks into your office.
Terrifying.
Yeah.
So
It's okay, it needs to be sharpened.
in theory, how would that even be used? I don't even see.
Oh, poorly. I mean, that's the whole shtick behind Star Trek. I mean, all of these battle scenes are not really well done. At least in the original series, and Next Generation, the real shows before it became a lot of action.
Mm-hmm.
It was more cerebral, but the action scenes were just hysterical. And maybe there's some people who can wield a Klingon batleth sword very well, but I don't think they were paying attention to how useful it would be, how effective it would be in a real battle. And you just get to watch these slow motion scenes, but it looks like an intimidating sword, and I love it. It says a lot about everything that motivated me throughout grad school.
So you didn't use it. You don't practice with it. You didn't sit there in the mirror and just.
Oh yeah, I've done it, and I've used it for a few Halloween costumes.
Of course.
It's fun. But no, I think I learned early on that's not going to ever be something I'd master.
Well, I can honestly say from personal experience that it definitely set the tone for how I expected this lab experience to go. And speaking of the lab, I say we just hop right into it. Let's talk about the Carlini group. Just a little intro of the research, what we do here, how everything got started. But first and foremost, what is the Carlini group to you?
The Carlini group, to me, is a very interdisciplinary research organization or research effort. In this way, we explore a lot of either structurally dynamic biomaterials or flexible devices. And the ultimate goal is to be able to have an autonomous controlled loop device that can sense a biological condition with the embedded chemistry and then respond accordingly. That could be through a change in the mechanics, a change in the shape, actuation with delivery of drugs. And so some of my drug delivery devices are ratiometric in that for every one molecule related to inflammation, such as a reactive oxygen species, you can have a release of one molecule of therapeutic or, say, an anti-inflammatory. And so you have this sense, response, and then ultimately feedback. And I really want my feedback to be a digital feedback that you can have on your phone, which would be something that a user would be able to identify or monitor over time, even if it was an implanted device. And we've got a lot of research that predates anything I've done in each areas of this. And my lab, though, wants to bring a lot of it together. And for the most part, I want to use engineering, but more synthetic chemistry as a way to introduce this modulation and encode the response behavior. Because, in my opinion, you can make very, very selective chemistries to various different redox agents, enzymes, narrowly defined acid responsive sensors, or mechanical sensors. So piezoelectrics are an interesting system that I'm working on right now.
So when you say piezoelectric, like what does that kind of mean to our listeners who don't fully understand how piezoelectric works?
Listeners or people in the room, perhaps. Just as an example.
Right. Okay, the simplest explanation I can think of is a material that can reversibly convert mechanical energy into electrical energy.
Mhm.
So if you take a piezoelectric material, it's a property of this material, say it's a film of PVDF, polyfluorovinylidene, polyvinylidene difluoride, which is piezoelectric. You can compress it or strain it in some way simply by pushing it, bending it, and this mechanical deformation causes a rearrangement of dipole bonds and this polarization of charge. Right, so the chemistry or the physics explanation is that you have this charge separation now across the surfaces of it, and then that can generate electrical potential. So if you push on it, it will generate electricity, essentially. And then inversely, you could apply a current to it, and then you could have a mechanical deformation. So maybe you can have the material expand in size or contract in size in response. So they're very useful. I mean, they're used all over in haptics. And we were talking about that earlier, right? Haptics are found in your cell phones most commonly, with any kind of vibrational feedback whenever you push a button, so that you can know you've actually pushed that button on your flat screen. They're used in your game controllers as a rumble pack, and they're used in soft robotics for prosthetic limbs, also to provide tactile sensation to people who are paraplegics or quadriplegics, to allow them to understand, to know touch and feel sensation and kind of map that back into their brain. But piezos are used also in energy harvesting.
Mm-hmm.
One of the coolest ideas that a friend of mine had kind of brainstormed a long time ago, early on in grad school, was this kind of a walkway, where a bunch of people in a crowded city street could walk across this sidewalk, which was just filled with these giant piezoelectric tiles, and then you would essentially be able to power the lights, and anything else around it. Well, they've actually done that, and I can't remember where in the world they've done that, but I read an article this past year where it's been done. So I like the idea of miniaturizing it and making it for implantable systems that could power themselves as biological sensors or dose regulators.
So the nature of piezoelectrics also just sounds interdisciplinary, because you have synthetic chemistry, just like the synthesis of it. You also have this kind of like this physics standpoint of kind of like finding the optimal like molecule arrangement that would give you the most electrical output, and then you also seem to have kind of like this engineering standpoint, like how much electricity can you actually get out of this kind of thing. So just the nature of the project already sounds like you need a variety of students to and their expertise.
The nature usually is to go from the beginning to the end, and one thing that's unique about what we're trying to do is that we're trying to approach the chemistries of flexible piezos. The field is quite advanced when it comes to the inorganics, that ceramic-based piezoelectrics that we use everywhere in normal technology, but the flexible systems always just pale in comparison to the performance, and a lot of strategies that are, I guess, geared towards improving piezoelectric response of polymer-based systems focus more on repackaging techniques. How can we take this existing polymer and spin coat it or electrospin it or pull it to allow the bonds to rotate such that you have increased dipole moments along each of those. But at the end of the day, it's kind of like throwing spaghetti at a wall and looking at the orientation of the polymers and saying, yeah, I think these are more aligned. And there are good strategies. There are synthetic strategies where they've completely changed up the chemistry and use different polymers, some that use gelatin or silk, nylon, a lot of biodegradable or biocompatible systems, but those usually have far worse piezoelectric properties than polyfluorinated polymers. So again, we're kind of at this stage where it's reproducibility, scalability, and synthetic difficulty can get in the way of making these robust systems that can compete with these ceramics, right? And the question is, well, why do we care to compete with ceramics? Well, the answer is that many of them are made of toxic materials. They're pretty brittle and rigid, so they may not be pretty good for implantable technologies where you need flexibility, bendability, or biocompatibility.
Mm.
And so that's kind of where the interdisciplinary nature comes into it. So like full circle, right, to your question was, yes, it does need to be highly interdisciplinary when you approach it from a polymer standpoint, because now we're going to completely not just redefine what chemistry we use, but their architecture, their organization, such that we can have molecular alignment at hopefully the angstrom level scale that you see with the inorganics that completely outcompete those of the polymer systems. And so you have to know polymer chemistry, obviously synthesis of the starting macromonomers or the individual molecules that you're using. You need to use engineering for device fabrication and any kind of data acquisition. You need to use materials chemistry to understand the properties of it, and then physics. You can use physics for modeling the behavior of these piezoelectrics so that we can actually predict what types of architectures and structures that we can predict, that we can design, that would enhance these piezoelectric properties.
So what got you into this field of research originally? Was it an undergrad thing, something you found in grad school, just sort of ideas you got like bouncing off from talking with friends, or like how did you kind of get into this?
The piezoelectrics project, or most of my work in general?
Most of your work in general.
Just generally your work, yeah.
I see I see myself as a person, chasing after that shiny red ball.
Mm-hmm.
I love seeing something that's new and interesting and difficult for me to understand in the beginning. A little overwhelming, and I hate not understanding why something works.
Mm-hmm.
So then I'll kind of pursue it. And I'll try to tackle it from a new angle that hasn't been addressed to solve problems that are still persistent.
What you studied in grad school is very different than what you study now, correct?
Yes, and what I did in my postdoc and what I did in my undergrad, right? Why did I do that? I kept getting excited about new endeavors that I had no idea of, and I treated a lot of it as a continuing education. The more I learned on different topics, the more I felt that I could communicate within different fields. You obviously run the risk of limiting how much of an expert you can be in one field, but you expand your horizons and your ability to conceptualize solutions. And so each time I went to a different stage of my life or my education, I focused on something, wildly different, with the expectation that I would incorporate that into my future, or what is now my current lab.
Mm-hmm.
So I, incorporate some modeling, but a lot of polymer chemistry and flexible device design into what we're trying to achieve here.
So, circling back, like what did you study in grad school and your postdoc, and even in your undergrad, and how is it trying to like start something new every single time, and starting fresh?
I'll start with the starting something fresh. There's this feeling every time I start something fresh and I commit to it or I have this thought of, oh God, what did I do? Why did I do this again? This is terrible. Why can't I just kind of coast or enjoy my existing level of expertise and knowledge and, improve upon that? Why can't I just become really, really good at this and have it be easy to crank out papers? Why did I have to go into something entirely different? And I feel like I could have gone either way, but I took on a harder challenge, in my opinion. I took on a challenge that I knew I'd never get bored of. But it's overwhelming sometimes. It's overwhelming because you're essentially starting over a PhD every time you switch fields. And you have to be the one to understand it. You have to read literature from an entirely different field of experts. So you have to know who they are, what their labs do. You have to understand where the state of the research is. And that's just starting over your PhD again. And then doing entirely different, either fabrication or synthetic, needing a whole new set of skills that your last set of skills may not have helped you with. So that is stressful and overwhelming because you only have a limited amount of time really to learn it all and then apply it, and then not just apply it but show the world that you've done something worthwhile. Now, if we go back, in undergrad, I was at Virginia Tech, and I got involved in a project that was purely computational modeling. So I built this genetic algorithm to study stochastic chaos, and it was all in the computer. And so that was this whole genetic algorithm, calculating the Opanoff exponents with a very, very simple mathematical model for chaos, this autocatalytor, which has just three major variables. And you use nonlinear dynamics to model it, and then seeing what variables for this nonlinear set of equations, actually causes the highest robustness to noise in the system. And it was pretty much a model of a biological cell and protein expression or gene expression. But at the end of the day, this was all in a computer. So I learned coding. I used my basic understanding of biology, but it was a lot more mathematics. And even though I was only a math minor, I was just really excited about it. I thought it was just really cool. I went to grad school, and I actually intended to continue doing computational modeling or computational biology, but ultimately that didn't work out. The advisor that I had wanted to join actually ended up leaving, and they were the only one really there on campus at UCSD that I had really explored and wanted to join labs with. So then I just thought, well, let's see what else is there. And like a kid with a shiny red ball, chasing after it, I found this lab involved with polymers and, making these crazy nanoparticle systems that could change shape in response to disease was really interesting, right? They would essentially flocculate together as these aggregated scaffolds, and at sites of cancer. And my advisor, who I was rotating with at the time, had pitched this idea. Well, what if we can do this with heart attack model? So I have a system a scaffold that could accumulate at the site of heart attack, and then potentially slowly elute therapeutic drugs afterwards. But it was challenging, right? Then I had to go into a lab that was synthetic. I had to understand polymers. I had to do tissue engineering. I ultimately, when I completely committed to it, I was doing animal studies as well, peptide synthesis, modeling of peptide sequences that would initiate really good hydrogelation, doing a lot of materials characterization and mechanical analysis. All of that together, in a very condensed PhD was difficult to do, right? And you post, but then I really wanted to learn about electronics partway through my PhD, and I told myself I wanted to learn from John Rogers' group, who does amazing work with flexible devices. And so I joined his lab pretty much the day after I finished my PhD work, and I went into his lab and just started an entirely different project that was all mostly making electronic thermal devices and sensing blood flow changes in response to disease.
So when you say that you were chasing this shiny red ball, do you think that you kind of like got to the red ball in each one of these scenarios?
I did. I did what I wanted to do. I wanted to do some computational modeling. I wanted to do polymer chemistry and tissue engineering. And then ultimately I wanted to learn just enough about circuits, electronics, and devices. More importantly, devices for translation aspects, because a lot of really nice chemistries may not be reproducible or scalable, or in general just translatable to technology and biomedicine. And these fields of implantable flexible devices with these biocompatible encapsulants like PDMS, using electronics flexible electronics that are embedded, those end up being having a lower barrier, in my opinion, to translation. And so if you can incorporate both of them, you can have this beautiful marriage.
To what degree would you say your emotional connection with the subjects affects your desire to work on them? Because I know obviously with something like biomedical devices, right, had some sort of emotional connection to that, it would probably make you want to do it even more.
That's a huge part of it. Having, believing in your work and continuing with it is what motivates you. I don't think I've ever lost interest in what I was doing. That's kind of not why I've chased the shiny red ball.
Right.
I've just wanted to add that to the list of to-do tasks. And now I think I'm pretty done chasing the shiny red ball of major areas to explore and, and exercise my interests in myself, right? Now I'll let my lab explore itself, but I think now we have to rein in the expertise to the knowledge and circle around these subfields. Never got bored of what I was doing, and I feel like I could have always kept expanding, and I never felt limited. I just think I worried that I would feel limited when I was in a faculty position where I could no longer devote significant amounts of time just in the lab to exploring, new chemistries, new engineering techniques, to see if I could do it.
Right.
It's a very different experience, knowing how to do it in the lab versus having other people do it for you. And I really wanted to make sure that by the time I got a job, I was well enough first to be able to help my students and my postdocs out.
I think that's an interesting thing to bring up, especially considering I would call it a rather unique, personnel list for your lab. And by that I mean the extremely high concentration of undergraduate students. How many undergrads are in your lab currently?
It could be about 15 right now. We had about 5 graduate recently. But we were, I think at max we were about 20.
Yeah. Is there some sort of specific reason that you wanted to have a lab like that? Did it just sort of happen? How did that kind of come about?
I think it was mostly strategic and unplanned. My goal is to have undergraduates always. I think undergraduates are very valuable, and I think it's very valuable for undergraduates to have research experience before they go into grad school or enter the job market. Lab classes can only teach you so much, and you've already got your other classes that you're so focused on that you treat these lab classes, unintentionally treat them like just another thing to figure out how to get an A with and not really absorb the material. And that happened with me as well. When you go into research where you don't know the answer and you don't know if there's an appropriate answer, you have to approach the problem from many different angles. And you have to think independently on how to solve a problem. And that's a whole other ballpark than what you're generally taught in your classes. Even if there are some really nice classes that teach you about research, just getting in and doing research is important. So I've always wanted undergraduates. I think I always wanted about 5. 5 at any one point, right? A student, and I would take a nice disperse array, right? Some that want to be really good at, say, one instrumental technique and are the super user, the super runner of certain experiments. That may be useful for industry. Others who want to do research, and they would team up either in groups of 2 to 3 with undergraduates on a project or with senior grad students. The reason why I ended up with so many, though, is because of a unique situation. I was trying to build a lab rapidly, and you could do that with new graduate students. But then you end up having them spend a whole year building a lab, and that's a year of their PhD. And there's only a limited number of grad students I could pay for, or bring in at once, such that I give them a meaningful work. For an undergrad, it's very useful to set up a lab and see how it works for, say 1 quarter before they even start with research. So I've started bringing in tons of undergrads, and they got to learn the ropes. They got to learn how to, fix an instrument that we would inherit, or set up a safety section, or inventory chemicals that we've inherited, or order new equipment and understand why, it's useful. And then do preliminary reactions, start synthesizing some of our small monomers. They're tangible projects that are really useful to the undergrad, but may not be extremely useful for a sole focus of grad student. I brought in a lot to get the lab going quickly, and I also wanted to build in a really nice social, environment. So a positive learning environment, which wasn't this quiet, high intensity and miserable experience of a lab where there's fewer people to brainstorm or bounce ideas off each other. So undergraduates were a very nice way to go to the lab quickly. And now what I'm working on is, once I've mentored them all individually, I'm not taking new undergraduates and I'm graduating them, and as you two are already involved, you've been involved for a while on different projects. And I mean, you've already published. One is a co-author, Nathan. And Ben, you guys are working on next paper for your subgroup. But as we continue, I want to narrow it down to 5 undergrads so I can continue mentoring. But I can also have now my upcoming rising graduate students who are getting more experience be able to take over mentorship skills.
So, when you have all these undergrads, usually when like a grad student comes into a lab, they kind of have this research experience under their belts, maybe from their undergrad, like a year or two. What's it like mentoring a bunch of like little kiddos that don't know like shit from Shinola in the lab?
What's funny is I think the pandemic pretty much made it such that many of the graduate students that are coming in are also in the same boat as the undergraduates, though. I mean, many of them may have had a technical understanding of how to do research. The ones who ended up doing the most research probably did modeling experiments or things that you could do on a computer. Some did isolated experiments, but it was not the way that I remember a lab being run, which involved just being in the lab, trying new things all day long, reading papers, and just getting your experiments set up the night before and running them first thing in the morning. So, you say new undergrads coming in with no experience. Sometimes I see that with grad students, and it's an interesting experience for me. I've definitely mentored undergraduates. I've mentored high school students and graduate students throughout my education. So I think just starting people off with the basics is useful. Obviously, I can't spend every waking second mentoring my students, and that's where I closely mentored my first subset with the expectation that they can help build SOPs, make instructional videos to help out upcoming students with things that do not require me physically being present to say, how do you run a rotovap? When it's something that you can easily just look at the video and follow along, such that by the time they come to me, I can help them out with more advanced techniques. It's definitely it's been really fun. It's a lot of time and investment though. Bringing in students who don't know enough, and I'm hoping it'll be a little bit easier as we continue on. Especially with the existing expertise that's built in the lab, these students who are more senior can now help train the students who are more junior.
Yeah, I mean I know me and Ben are for sure grateful for the opportunity, but can you talk more about like what it was like kind of starting a lab? Because you just finished your first year at UCSB, so like what was it like starting a lab? What was your first year like, and like what do you think you've learned the most from the experience of being a professor for a year?
Okay, so I'd say I started with a lab that I inherited quite a bit of materials, supplies, equipment.
Shout out Galen Stuckey.
Yes,
We'll definitely put up some pictures right about now for future Ben editing this. Definitely, I know exactly where the photos are and which ones to put up.
Yeah. So I mean, this is a lab that is world famous, has produced an insurmountable amount of work, and has just been a powerhouse. And it's really an honor to take over a lot of the space and a lot of the instrumentation that and continue work using what they have built. It comes with its own caveats, right? Much of the equipment was in states of disrepair, and a lot of the chemicals were either expired or in bottles that would just disintegrate in your hands. And so, having to go through such a large inventory was one of the motivations for bringing in new students. Obviously, once I was able to identify and remove any excessive hazards, it's just, comes with the territory of inheriting so much. I could have not inherited anything and then had to pay for all of that with my startup, and that would have just drained my startup. So I would say I'm pretty lucky in that aspect that I had, a senior faculty member pass down a lot of what they had. And then, but a lot of work, a ton of work, right? Every day you come in and you think, which thing do I have to do first? What would be best? Okay, I've got to develop a lesson plan for the classes I'm teaching, right? Especially if it's a new course I'm designing. I have to figure out how to teach a course, how to, put together a syllabus and design each module, make sure I have the right number of assessments planned out. Then, how do I do preliminary experiments that I can teach my students, or that can test, or at least begin to test some of my hypotheses of the project I did propose to do? How do I get involved with a lot of the outreach and service and departmental administration work that is just required of new faculty, learning the ropes, learning where do you get resources, who has shared facilities, who are the people to contact, do I get trained or can I get other people trained, accessing just purchasing, going through the purchasing portals and start buying equipment and materials, and making sure that I'm not going to completely spend through my entire budget. And then, thinking about grants to start raising funds, right? So that I don't have to continue to tap into my startup funding, which is arguably some of the most flexible funding I will ever get. So I just want to raise money, and then I also want to recruit new students and mentor them, and reassure them that I can provide a good, PhD for them, and a good learning experience, as well as a huge number of skills that they can take into the job market, whether or not they go into academia, industry, nonprofit, government, in law, anything like that, and getting involved with service and outreach. So juggling all those things together with a lab that is completely non-functional and students who look to you for answers to big and small questions ends up completely destroying your ability to organize your day. So I feel like it was just putting out fires of the most pressing manner. But obviously starting the research up was the most important, right? Once I was able to get that to be somewhat self-sustained, I was able to focus on other aspects of the job. But yeah, it was chaos, and it still kind of is. That being said, I think that's why I love it. I love chasing the shiny red ball of some new task to do that I haven't done before, that I intend to get really good at and really efficient at. And that's the reason why I went into academia over other fields. Because I love the variety, I love the ability to control, how I direct my day-to-day activities, and to keep it interesting and fresh, because otherwise you're spending 50% of every single day for the rest of your life essentially doing some repetitive task for other people, guided by money maybe.
Do you ever find it difficult, like, forcing yourself to take the hands off? You know what I mean?
Oh yeah. No. I've been a control freak in the past. Handing the reins over was definitely difficult, and it's one of the things I anticipated but hadn't quite experienced enough to fully know it, and I knew, right, I would just have to let it happen. I would have to trust that my students would learn the way that I learned, rather than hover over each one and critique every little thing in the moment and spend so much time critiquing them. And rather waiting until we had our meetings, or until I kind of came in to do rapid critiquing, but directing them elsewhere and saying, okay, you can learn that from this person, you can learn that from this web resource, you need to just look into that, and then come to me with proposed solutions. Read the current literature. Eventually, once I felt confident that my students could do that background research, I felt that it was okay to give them a little bit more control of their projects. And it helps having them in groups, right? And bringing in senior experts, such as postdocs and collaborators.
I mean, yeah, back to the critiquing thing. I think one thing that whenever we give a presentation to the group, one thing that we always start shaking in our boots to hear is, can you go back to that slide really quickly? And then we all just say, oh, shit.
What did I miss? What did I forget to add?
Oh yeah, and it's an interesting balancing game, right? Because of course I want to nitpick everything, and I want you to change all the things that you've done wrong or that I want different, which may just be very subjective. I want you to, get better and better. But at what point am I just going to overwhelm you with, critique and criticism that you won't be able to improve? So I think I increasingly criticize more and more senior students, and as I go on, I expect any of the small changes that I suggested to always be implemented.
Right.
And then I give you more challenging changes to implement, and I expect more and more out of you.
Mhm.
And balancing that, versus having a student burn out too quickly is definitely a concern, right?
Right.
I want to always push a student to be the best they can, but I also don't want them to just burn out and say, no, I don't need this, I'm gone, and then they miss out on really becoming a stellar scientist later on.
Mhm.
And that's it's very individualized. I have to individualize my mentorship to each student based on how they respond, because no one's the same. No one has the same background, and each person has their own limit.
Mhm. I mean, I think we've asked you, well, I've asked you this before when you were slightly more indisposed at a trivia night, but I want to ask you this again now for the listener. I kind of wanted to ask you, I mean, you talk about pushing your students. What do you really want your students to get the most out of the research experience? When they come, you want a student to come through the Carlini group, maybe when they're green, and then when they leave, like, what do you want them to have with them?
I like the ability of them having a set number of skills that they can say, yeah, I'm really good at these 3 techniques, but to be honest, the best thing is to learn how to tackle the unknown. If a student can work independently or independently address an unknown question, that may take a solution of, 5 different, 5 different things that all converge together. I want them to be able to just be addressed with a complex question and then say, okay, I don't know how to do it, but I'm going to try to figure it out. Here are the initial clues, and here are the experts I can look to. I'll go do the background research. And now that I know how to read a paper, and then I will, contact these people, or either on campus, off campus, and get information, or at least I can work with my PI to direct it. So how can you direct your research ultimately? And obviously you have mentors who work with you, but I shouldn't just be your teacher that spoon feeds you everything.
Yeah.
And when you leave this, when you leave the academic environment, it's expected that you are an independent individual who can do all the same things. And if you can't, you will know how to address it and how to approach it. So it's this independence to work and address an unknown problem without fear or stalling and expecting the rest of the world to help you out.
Right.
That's the most important skill, I think.
Since we're on the subject of undergrads, I want to talk a little bit more about your own personal undergraduate experience. We understand that you triple majored in chem, biochem, and bio, and you had a minor in math. Are you a masochist? Do you like pain? Are you someone who approaches? What was sort of the motivator behind spreading yourself amongst all these different kind of sort of related but ultimately pretty disparate topics?
Yeah, you'd be shocked how much extra coursework you need, or wildly different coursework there is when you compare, say, biochemistry versus biology versus a chemistry degree.
Right.
In say one university versus another. And at Virginia Tech, each of those had a wide array of classes, and I was just really excited about learning. Right. I thought I've got only 4 years to take these courses because I couldn't pay for more, and I had to pay through for my college with a lot of scholarships and of course as few loans as possible. And so I was having to direct that and not having someone else give you the money for the education is a big motivator for getting your money's worth, essentially, right? And I didn't want to coast. I went to college right at the beginning of a recession, and people were losing their jobs, getting laid off. They had all done the right thing, right? They went to college, they got their degree, then they went into industry, and they did their work. They put in their time. They learned and output the right amount of data. And at the end of the day, it wasn't enough.
Right.
And they were chopped. The people who were kept were the people who'd gone above and beyond, who diversified themselves also and put themselves in positions of leadership or in indispensable positions where they couldn't be replaced. And so I was motivated to be that person that would never lose their job, because it was a very scary concept.
Yeah.
To push yourself and do everything right in society and still have everything taken away and just be punished because politics or other people in finance made very selfish or completely risky decisions. And so I just didn't want to be controlled by that. I definitely determined I wanted to be a professor, probably graduating high school, definitely go into research, and I just worked towards that. And so I wanted to be the best, I wanted to get the best grades, I wanted to be the president of however many different organizations so that I could exercise leadership, because I hated public speaking, I hated being in the spotlight. And so I figured I had to force myself to do things that I hated in order to either start enjoying or get past.
Here we are putting you in public speaking and the spotlight right now.
Yeah. Or at least we're not doing the camera, right?
Yeah. So it seems like you just have, like, instead of being a masochist, as Ben said, that you just kind of you had that go-getter, like do anything by any means necessary kind of attitude going to any of your projects. But
yeah, my dad would always say growing up, you can do anything you put your mind to, and as long as you keep using your mind, you'll have more power than you know what to do with. And so you'll have freedom to control your life if you keep using your mind.
Well, I think that's something related to something you once said to me one time, where you said, if you're going to take a risk, be ready to work twice as hard to make it happen. And that was pretty good. But kind of transitioning, like what with all of that to do, maybe as an undergrad, as a grad student, you kind of worked super hard. Like what would an average weekend for you look like?
Or just any time away
from
everything.
From being busy.
Back when I was in school or now?
In undergrad.
Okay.
Over 21, of course.
It changes. I mean, I can't maintain that indefinitely. I mean, life changes, personal life, is affected, family life, everything. So, and I had a lot of anxiety, so I have periods of extreme productivity and periods of very low productivity for my own standards. And instead of being frustrated with it and letting it take me down, I now kind of reorganize my schedule such that I can set easy tasks to motivate me on days when I'm really really, really low energy, whereas, high energy days I have no problems with it. I always make sure, though, I don't regret, wasting so much time, because I would spend, 72 hours in this math emporium or in a library, just with changes of clothes in my backpack and, maybe some face wash and deodorant, to kind of have a semblance of a miniature bath without having to go home when I needed to crank out a lot. But when I had better schedules, which I'm now much better at, I make sure to do at least one day of really fun, stuff, or just to be lazy and, watch TV, or, maybe I'll paint a picture, or I'll go out on a hike, or, just try something brand new, maybe some social event. But in college, I don't think I had mastered that. I had a weird series of schedules that was just entirely defined around homework deadlines, exam deadlines, and anything related to the outreach that I did. So I would say I mostly just worked. Mostly worked and studied. I had this futon that I spent most of my time on. And I had a semicircle of textbooks that I'd have open around me. And I would just work on each assignment or each whatever in each class and keep going and just keep turning, the circle. And but when I did enjoy myself, I would make sure that it kind of multitasked in the way that, if I wanted to go on a big hike, I was chemistry president, I would, organize the chemistry hike. And so we'd go out with a bunch of our friends and just, enjoyed hiking down the Appalachian Mountains. Or, if I really wanted to go to do something social, right, I would try to get myself to a conference. I would apply for a travel award, go to a conference, talk to people about my work, learn about their work, but also just enjoy it. It's good to explore a new area, get on a plane somewhere. Yeah. And then, of course, partying hard. Work hard, play hard. I definitely blew off a lot of steam whenever I needed to. So.
Yeah.
Would you say you've had a harder time mastering having fun than you have mastering any other real disciplines?
No, not really. Not really. I'm pretty good at entertaining myself. Growing up, I lived in a very wooded area that was surrounded by nature, but not by a lot of other people. So I didn't really hang out with a lot of people. And some people would just consider that boring and be miserable. I loved whatever I set my mind to. So I would go wander the woods, pick blackberries, or raise insects in these terrariums and watch, how they underwent metamorphosis.
Oh wow.
And then I would pick up painting, or I would tinker with things that I'd find in the garage. I'm very self-sufficient, and so I've never had a problem having fun. And I'll go do something random that I've never done before, and that's just fun for me. So I don't think I've ever had that problem. I think the people who feel they don't they expect. I think they expect a certain level of fun or whatever to feel, happy, or they feel like they've reset and recharged themselves.
They need some threshold that needs to be surpassed.
Yeah, maybe they have to go out and hang out with friends at a bar, and they can't have fun unless they do that. But I can do that and enjoy it, but I don't have to do that every time. Whenever I'm feeling like I've neglected my personal fun. So I really just enjoy exploring anything as a new task, even if it's just building something new.
Yeah, I love what you said about the bugs in the jars. I feel like that's the classic, ask any Nobel laureate how they got into science, and it's I looked at bugs in my yard, or I looked at flowers or something. I feel like it's always how it starts.
Don't compare me to a Nobel laureate.
Well, you get the idea. They say on the website, and it's funny that I've never noticed this before, that there's a quote at the bottom of your personal page that says nature is your endless inspiration, which I think is really powerful. Can you speak a little bit more on that? What do you mean by that exactly?
I obviously believe in evolution and natural selection, and I read On the Origin of Species by Charles Darwin, and I think that had a profound impact on how I see the world. And I think that no matter how amazing the new chemistries and new knowledge we learn from mimicking nature, at the end of the day, we're mimicking nature because it has produced so much that's so complex. A lot of biodiversity with regards to plants, various living organisms. How do plate tectonics, work in forming new mountain ranges, and how we view what the fossil record is, because maybe a lot of the oldest fossils have just kind of been buried now under the sea. But I've just been excited about the unknown, and just at this point we cannot do enough to even compare to the complexity and power that nature has. Just because we don't know enough yet, right? We may surpass nature's ability to increase complexity, but until then, that's tangible. It's something I can collect immediately, or I can observe immediately, because it's all around me. So usually when I'm walking around, I'm just looking up at trees, and the sky beyond it, or looking down at an individual fern leaf, looking at how many variegations there are in the leaves, and then asking myself, why was that selected for in this environment?
Yeah.
Or why did that not get selected against? And or I look at ginkgo leaves and I think, this is one of the few living organisms that came back after the bombing of Hiroshima, and so the atomic bomb sets off and there's radiation poisoning everywhere, and yet this organism can withstand radiation poisoning and has genetically been conserved for hundreds of millions of years, right? We see ginkgo leaves in the fossil record, hundreds of millions of years old, unaltered, because obviously it's been able to survive, all over the planet, different climates, different times, and it just still has not been wiped out.
Yeah.
So how do you create something so robust?
I think my personal favorite example of that, of like natural selection, what you were talking about, where you look at these things and you think, why was that selected for? Why is that the thing that is ultimately defined this species? Is the quaking aspens, where their root structures are all connected underneath.
Yeah.
So instead of being like one singular tree, it'll be a whole field of them will be one singular organism, to the point where if you shake one tree, the vibration will follow the root structure to maybe not to all the other trees, but other trees in this grove will shake in response to you shaking the one that you're like touching. And
almost like some mycelial network.
Exactly.
In Last of Us, right? The zombie show that just came out, and that's based on the video game. It's Last of Us, right?
I haven't watched that.
That's really funny that you said mycelial network and you didn't say that, and you didn't think about the zombie movie.
How this like interconnected sort of like network. It's like kind of like a hive mind, basically.
Yeah, aren't those aspens considered technically the oldest living trees, because the root system's connected throughout, and so
they also produce the heaviest and largest singular organisms on the planet, because it'll be these whole groves of trees that are
that's the largest.
Tend to be one singular organism.
Yeah.
Like billions and billions of pounds of just like root.
Just roots.
Just roots.
Well, mycelial network though is just like, I think we think about that from fungi aspect, right?
Yeah.
Yeah, so it's different than plants. But yeah, I mean, I hadn't watched the TV show, but I mean, we know about mycelial networks through biology.
Mm-hmm. So you've taught a class kind of on synthesis of biomolecules, right? Synthesis of biomolecules. So that's molecules.
The chemical synthesis of biological molecules.
So those are molecules that are found in nature that you are synthesizing in the lab or modifying in the lab.
Yeah, specifically polymers. Biopolymers, like DNA, RNA, polysaccharides, peptides, proteins. What nature produces in the aspect with multiple repeats of kind of building blocks. So kind of click together Legos, because those polymers have way more complex behavior than small molecules in most cases, and that's kind of why DNA is part of our genetic encoding.
So we like to start a segment we like to call Blue Book. We have one of your old test questions here, and we like to ask you this test question and see if you can get it right.
Probably won't.
That's good content.
This is great content then. Brandon Green got it wrong when we asked him one of his old test questions. So the question is, define the key differences between the grafting to, grafting from, and grafting through strategies. And you ask for 3 to 5 sentences, but we're not going to make you say 3 to 5 sentences here. We're a little bit easier graders than you are.
For 1 point.
For one point, yeah.
Okay, grafting to, you can essentially have a pre-made polymer and you can conjugate that to either another polymer or a surface. Grafting from could mean that you're polymerizing off of a substrate or off of another polymer. And then grafting through may actually mean creating a macromonomer and polymerizing any number of small monomers and as well as large macromonomers, which may in themselves be a polymer, but with a reactive head group, like a warhead that you can polymerize. And all of these are advantageous for creating complex polymer architectures, but some of them you may need different strategies depending on the conditions, right? And if you have a protein you want to polymerize or add a polymer to, you really don't want to subject that protein, which can misfold, to a really tough synthetic environment, which so you may actually want to use kind of click chemistry to append a new polymer to it, or maybe it's sterically hindered, so you can't do that. then you may actually have to polymerize off of it using a polymerization strategy in water that doesn't promote degradation. So, long-winded answer.
Mm. Well, you got it right.
Oh, okay.
You got a point.
Ding point.
So for extra,
Point me, green 0.
So for extra credit, you were a math minor in your undergraduate, correct?
Yes.
So we have an integral for you to solve.
Oh, this is where you're getting me.
Okay.
Remember, it's like over 10 years since I've had to use any really.
Oh, you can use the back of my question paper, a scratch paper. It's the integral of x times sine x. Here, you can use this as scratch paper.
Oh, that's so easy back in the day.
And remember, this is an audio podcast.
Yeah, thank you. No, I can't remember. I feel like it would have been cosine x plus something or whatever.
C.
Well, plus c, yeah, constant. But I would just tell you right now. I'd have to look back at my cheat sheet to use integrals, and that's kind of something that I have to do soon. It's weird. My dad explained this to me, and he said, some things that you learn, you'll never forget. But other things, you have to continuously practice it or else you lose it. And he said math was the number one thing that you'll just completely forget. You can get back to it, but you need practice. And even when it comes to skills, I've painted and played the violin for long periods of time. And painting, I could pick that up 10 years without even trying and be pretty good at it. Playing the violin, I'm absolute garbage at now.
Mm-hmm.
I was never absolutely amazing, but I got fairly good with regards to my level of expectation. And now, I'd be happy to do some scales and redo some in middle school.
That was a cat walking by something, everybody.
Yeah, Tara loves doing things like that.
The podcast.
Just kidding.
We'll post pictures of Tara now. She's adorable.
So for anybody listening at home, yes, you do not need to know the integral of x sine x to be a professor.
Remind me the answer.
Negative x cosine x plus sine x plus c. So you have to integrate by parts, and then you'll get the answer.
Yeah. Now I'm remembering that. Nope, I would not have gotten that.
Okay, good thing that was an extra credit question.
Extremely loud, incorrect buzzer added here.
Yeah.
I like that you brought up constantly having to relearn things. Like you do it and you kind of get it in your head and then it goes away. I feel like as somebody studying chemistry or just studying science in general, there are so many things obviously that come up repeatedly in different classes, different concepts. And I always feel like every time I start a new class, even if I was just in it the quarter before, I have to go back again. And I feel like that's always, to a certain degree, can be kind of dissatisfying. Like, I learned this, why won't it just stay? Why can't it just stay in my head? And I know I can't be the only one that feels that way. So I appreciate that you, have the same sort of sentiment. For me, at least, this is going to sound stupid. For some reason, in my head, I can never pin down acid-base chemistry in my head for more than 5 seconds. Like I'll know it, and then it'll just go away. And I tried every trick in the book, every acronym and this and that, and stupid learning trick that they tell you, and it will not stay in my brain for more than 30 seconds.
Yeah, sometimes it's about the way you learned it. If you're a visual learner like me, you have to see it. If you can conceptualize it, maybe that was the best way to go. Other times, it's hard to do it without an example, right? Mm-hmm. You try and pure memorization without applying it, so you can't understand the moving parts.
Right.
So if you end up doing research in it for a while, it actually helps you remember it, and not just remember it, but understand it, because you're taught so much in your class, it's just to brute memorize everything.
Yeah, definitely.
And maybe if you change one number, you still plug it into that equation you have on your cheat sheet, but you don't understand how the equation was made. Mm-hmm. And that could go back to just reading that section in the textbook that most people skip. Where they talk about the scientists tinkering around in their own in their own rooms, trying to understand, well, okay, why does gas expand if you heat it? Is the proportion the same? What are the major questions? And then how did they derive the equation? Mm. And if you can't derive an equation, you're just focusing purely on memorization, and it's not going to serve you very well. So it's definitely annoying that you've forgotten the things you learn, and then you have to continue applying the things you've forgotten to your future.
Mhm.
And that's kind of where you have to just build in really good notes that you just review quickly over and over again with repetition and with use.
Yeah.
And if you know something you're just going to forget, go with it. I mean, now once you leave academia, right, you're not going to have everything memorized. If you want a refresher to use something that you haven't used in 5 years, you can go to the internet, quickly look it up, and then be like, okay, now I remember that. Okay, and then it helps you with your ongoing problem. But what you learned was what was the technique, or what was the equation, or what class you even learned it in to address that problem.
Mm.
And that's, in my opinion, a little more important, and being able to derive the base equation is very important.
Study your Henderson Hasselbalch's, man.
Yeah, she is.
Yeah.
And some of us have great memories, some of us have terrible memories.
I think
And so just find whatever works for you. You'll find something that works best for you that won't work well for another person.
I find that's one of the reasons why I really like chemistry, specifically more than biology, at least from like an undergrad learning perspective, is that I feel like so much of biology is just like flashcards. Just
Yeah.
like,
Oh yeah.
question, answer, question, answer, question, answer, and it's so hard to feel
Welcome
that
to
there's
med school,
some
right?
sort of
Yeah.
exactly there's some sort of connection between them, and that's why I like chemistry, is that at the end of the day, even if what you're looking at feels wildly complicated, it ultimately falls back to these like super common sense principles, at least common sense once you've sort of seen them in action.
Yeah.
That you can always like go back and then build forward to. Whereas with like biology or like history or any other sort of thing like that, you either know it or you just don't. You know what I mean? You're not. There's no like fundamental theories of basic science you can fall back to remember like what year something happened. You know what I mean?
Well, you can use tricks, right?
Yeah.
If you know, if you're trying to figure out what year some small war occurred, but you know what the outfits looked like, or if you know what weaponry they used, you could say, okay, if they stopped using it, to yourself, like, oh, actually, I do know what era they stopped using these instruments, or or if there was a fight over a certain territory, right? You may say, okay, wait, was that a territory? Was that a state? Was that a country at the time? Was it, was a state ratified at the time? If we're talking about American history, and then you can kind of distill back, and say, oh, okay, well, they used muskets, so clearly well before World War One. That may be Civil War era or anywhere in this range. Or, if you say, okay, first machine guns, you're like, oh, okay, that's definitely World War One.
You and weapons, I swear, the sword on your wall.
I'm interested in technology, and I would say World War One was my favorite era, just because
What is your favorite era?
Favorite war era to study,
Okay.
because so much technology came out at that time that was
Totally.
wildly innovative, even if it's just an absolutely horrible time in our past. What you learned from it was interesting, right? You learned and this was all defense, and I'm not necessarily a big proponent of of military and defense efforts ongoing, but it's interesting to see that huge boosts in technology came about in times of crisis.
Yeah. Especially like biochemically at that time.
Yeah, and that's not necessarily limited to war, right? It's just it defined an era where we kind of went through a surge in development, and that could have also stemmed from an agricultural revolution or an industrial revolution, where it's completely marred by terrible outcomes and mismanagement. But you still can't discount the fact that a lot of progress was made in human development.
Of course.
And, I think about how often society has just developed and then completely forgotten everything, through the fall of, a fall of an empire, potentially in the past, and how we've had to relearn everything ourselves and say that it was first discovered, at this point, because we've lost everything in history, and we kind of just retake credit for probably many things that were partially or potentially well understood in the past. And those could be select examples, but yeah, I'm interested in major pushes, in the world,
Yeah.
where we've needed to adapt.
Yeah, you talked about how like in times of crisis and in times of kind of like uncertainty, science has really developed. So kind of have like a stupid question prepared for you.
Nothing stupid unless it's stupid, right?
Yeah, I mean,
Well,
we'll see after we
it's
ask the
pretty
question. So,
Probably not.
so going based off, science kind of develops out of this time of uncertainty. If one of your students came to you and said they had superpowers, how would you use your biomedical research knowledge to kind of assess them, test them, and would you publish?
If a student came to me and said that they had superpowers, I would drop everything, maybe get a coffee, and then just sit them down and ask them, what are your superpowers? Can you please demonstrate them for me? And convince me. Because I would love to see a student fly or, teleport or whatever. Or if they're going to just show me an interesting little magic trick. But that would be fun. Maybe I would record it if they were okay with that. I would be humored mostly. And I would, so I would, swallow my pride if I was wrong.
Would you make them
But
a
I mean,
super suit?
why would I publish on something, like, unless it's a real superpower, I don't just, I mean, what superpower are we envisioning? Because I feel like you've jumped the gun there, like, oh, well, I make so many news announcements and like put my students to the test. I mean, chances are, if anything got out, it would be way out of my hands
Yeah.
by then.
It's a
And
meal.
no
A
student
meal
would
can
come to me.
fly. That's what it is.
Yeah.
A meal can
A
fly.
meal can now fly.
Would you
Does
make
he
him
know
a
this
super
yet?
suit? I hope so. Yeah. Would you make him a super suit?
I could.
I think a meal would look
I
great
mean,
as
are you
that.
thinking
That's-
about these shows where there's this one person who can develop the cure, the vaccine in an hour, and they say, oh, I can't do it, I need at least like 100 people to help me in 3 months, and then someone else just says, well, it's just you, get it done in 2 hours, and somehow at the end of the episode they get it done, and then that's what society views science as, and they'll just say, but this person's a genius. No. Just no. I couldn't even begin to address that, and how would I even take credit for someone else's powers, It would just be out of my hands.
Yeah.
There would be some large organization, government organization, whatever that takes over.
So you're not
If
Tony
so-
Stark.
Yeah, no.
You're not
No one
Bruce
is
Banner.
Tony Stark, and if anyone's really Tony Stark, it's definitely not the people we hear about.
Yeah, that's good. Yeah,
It's
very
their
good.
scientists that that work in the dark, and it's teams of people.
Yeah, I mean, it's super collaborative. Everything that everybody does, right? Like even most of your papers, you collaborate. You ask professors from different departments their expertise.
Yeah.
Right? Yeah.
Yeah, and I ask for help. We do a lot of background research, but I mean, if there was someone like that, I think society would get together, and there would be a big push for technology and innovation. And also, God, it's a student of mine, having powers. I mean, just the ethics of subjecting them to testing like that. It's a big question that I'm not sure I would even be prepared to handle. But they're the first person to ask me that question.
Yeah, I thought it would be a good question to ask. It'd be like in like the Flash where like he like goes to like the biggest lab in the city and he's like, I need you to help me out. Yeah. Yeah, but like what you were saying about the kind of culture around like society and science, like well, how would you kind of like bridge, I guess, the deep trust/distrust dynamic between society and science as a whole?
I'd say communication. I mean, some of our best science advocates and science communicators, may not necessarily have the most exciting active research lives, but that's because they devote themselves to communicating properly what other scientists are doing. And it's not just going out there and telling the world, but it's trying to translate from the technical scientific jargon that we use and surround ourselves by into layman's terms for anyone, even in other fields of science, to understand easily. Because at the end of the day, you should be able to say what you're doing without overly complicated terms. And there's just this negative impression in general society sometimes where, I don't know, I guess maybe we think we're better than others, or it's just, you have to be so smart to get it done, but in reality, it's just about drive. And, if you devote yourself to this, anyone can kind of, be a scientist. And I think there's this negative perception about things being hidden too much because, you can't, maybe some people are just not good at effectively communicating their work, or if there's patents, if money's involved, then it's all about hiding the idea, the details, so that other competitors can't take the idea and sell the same product for less money, or patent it themselves and get ownership and rights and royalties from it.
If any ad people are listening, we will sell out. I have no qualms about that
But
at
preferably
all.
to a caffeine company.
Preferably to somebody who will give me products I'll actually use.
Have you heard about the alien thing going on in the news right now?
Oh, that someone from the military had seen some UFO,
Yeah.
the size of a football field, hovering over some Air Force base or something
Yeah.
like that.
Yeah, what do you think about that?
I think that I have absolutely no information.
Yeah.
And that the rest of society doesn't. And so what are we doing? We keep hearing in the news the same story, which makes no sense, has no details, and is based on some useless press conference here and there. Nothing that'll be released because it's top secret news, whatever. And so what does the viewer do? Well, okay, the reader or the viewer had just enough information to get excited, and then where do they find their information? Well, the only people talking about it are probably people who are conjecturing and bringing in completely unrelated or irrelevant data. Maybe there's some relevant data, but it's all just getting thrown together in this giant soup that is this mixing pot and giant think tank of experts, non-experts, and I don't even know who's doing what, and these stories build themselves. And so it's just unnecessarily inflammatory, a ridiculous press hearing that just gave you enough to let society just blow up, on the side. Could be, a distraction mechanism. It could just be because it was needed. They needed to have a hearing because they agreed to it, and then they were just done with it, and it's nothing. But because we don't have enough information, why am I going to waste all day long trying to poorly hypothesize based on absolutely no real evidence?
Yeah.
What's going on? It's a waste of my time. It's a waste for society. It's a drag. And people who spend all day long trying to figure that out, they're just wasting their lives doing nothing productive.
Yeah.
In my opinion.
It could be one of your when you said you had like a lazy day. It could be your project on a lazy day is to think about the aliens.
Yeah.
I'm
I mean, if you're a
totally
good
new.
investigative journalist, then that'd be
aliens.
your job, and that's productive. But if that's not your forte, and you're just sitting at home, trolling everyone. Well, trolling's a whole other thing. That's kind of fun, but I don't do that. But I still enjoy sometimes when trolling happens, which obviously causes its own problems. But I mean, if you're just sitting at home, if you've got no formal training in this, and you're just riling other people up, it's really just a waste of your time and other people's time. And you can just have that midlife crisis and either have to convince yourself you've done something productive for society, or have that midlife crisis, realizing what have I done with my life?
Whew.
Yeah, jeez.
Ouch.
Rough.
Ouch.
So, Dr. Carlini, we really, really appreciate your time here. We've had a great time recording. We've been recording for a lot longer than we anticipated. We really appreciate all your advice and all your time. We want to leave off with one last question, just a question we ask all of our guests prior and going forward is, if you had to give any advice to undergrads in terms of getting involved with research or, setting themselves up for success, what would be like your kind of little blurb to give them?
Don't coast. You go to college. I mean, it used to be that you could go to college to get a degree, and that was enough. Obviously, now it's not enough to just get the degree. If you really want to set yourself up for success, differentiate yourself. Push yourself to learn everything you can, because these institutions are not just about taking classes like you did in high school. These institutions offer quite a bit of opportunities, and this is 4 years that you have the ability to do whatever you want. And so really, really focus on that. I know it's your first time that you have freedom maybe from your house, but also it's the opportunity you'll regret not doing better at.
Absolutely.
Excellent. Well, we really appreciate it.
Thank you so much.
Thank you so much, ladies and gentlemen. Dr. Andrea Carlini. For the second episode of the pH14, a very basic podcast. We appreciate everybody listening. Hope you all have a wonderful day. And yeah, any last words from anybody? Any final remarks, Dr. Carlini? Anything?
Aliens. I'm just kidding.
No, thank you for having me on here.
Of course,
Absolutely.
Yeah.